AI for renewable energy. Part 1: The renewable energy landscape. Powering a sustainable tomorrow. The 21st century faces a defining challenge, transitioning from a fossil-fueled world to a sustainable one. At the heart of this transformation is renewable energy, a set of technologies designed to harness naturally replenished sources like the sun, wind, and water. Unlike coal, oil, and gas, these sources are not only cleaner, but also virtually inexhaustible. As climate change accelerates and energy demands surge, renewable energy is not just an option, it is a necessity. But while the promise is real, so are the challenges. Renewable energy sources can be intermittent, dependent on natural cycles, and difficult to store. Moreover, integrating these sources into aging power grids and scaling them to meet global needs requires innovation, planning, and a touch of brilliance. That's where artificial intelligence, AI, comes in, a transformative tool poised to unlock the true potential of renewable energy. Before diving into how AI can reshape the renewable energy sector, it's essential to understand the landscape we're working with. The Big Five of renewable energy. 1. Solar energy. Solar energy captures the sun's rays using photovoltaic (PV) panels or solar thermal collectors. It's one of the most rapidly expanding forms of energy worldwide. Countries like China, the US, and India are leading solar adoption, building massive solar farms that can power entire cities. However, solar power is weather-dependent and only generates electricity during the day. Without proper storage or smart grid integration, energy supply can fluctuate dramatically. 2. Wind energy. Wind turbines convert kinetic energy from wind into electricity. Onshore and offshore wind farms have become iconic symbols of the clean energy movement. Some wind turbines now exceed 250 meters in height and generate enough electricity for thousands of homes. Still, wind is unpredictable. No wind means no power. Even in windy regions, output can vary hour by hour, posing challenges for consistent power delivery. 3. Hydropower. Hydropower harnesses the movement of water, usually from rivers or dams, to generate electricity. It's the most mature and widely used renewable energy source. It provides stable, on-demand power and also supports energy storage through pumped storage systems. Yet, hydropower isn't free from environmental and social issues. Large-scale dams can disrupt ecosystems and displace communities. 4. Geothermal energy. Geothermal energy uses heat from beneath the Earth's surface to produce electricity or provide direct heating. This source is remarkably stable and not weather-dependent, making it a reliable complement to other renewables. However, it's geographically limited to areas with significant geothermal activity, such as Iceland, Kenya, or parts of the western U.S. 5. Biomass and bioenergy. Biomass involves burning organic materials, like wood, agricultural waste, or even algae to produce energy. While it can be renewable, it's also controversial, as it may contribute to deforestation and emissions if not managed sustainably. The intermittency challenge. A major hurdle for renewable energy is its intermittency. Unlike fossil fuels, which can be burned on demand, solar and wind power are dictated by nature's schedule. The sun doesn't always shine, and the wind doesn't always blow. This unpredictability leads to gaps between energy supply and demand. Energy storage systems like lithium-ion batteries help bridge this gap, but they're costly, have finite lifespans, and introduce new environmental concerns, e.g. mining rare materials. Balancing these supply-demand swings is one of the biggest technical challenges in the renewable energy sector today. The infrastructure puzzle. Today's energy grid was designed for a one-way flow of electricity, from large power plants to homes and businesses. But with renewables, power generation becomes decentralized. Rooftop solar, community wind, and off-grid systems flip the traditional model on its head. This creates a complex web of microgenerators and fluctuating inputs that legacy grids aren't equipped to manage. Modernizing these grids, making them smart, is essential for a renewable-powered future. Global momentum. Despite the hurdles, the renewable energy revolution is underway. The International Energy Agency, IEA, reports that renewables accounted for nearly 30% of global electricity generation in 2023, and that number is climbing. Government policies, falling costs, and public support are accelerating the transition. Countries are also committing to ambitious targets. The European Union aims for 42.5% renewable energy by 2030. The US targets 100% clean electricity by 2035. India plans 500 gigawatts of renewable capacity by 2030. Yet, meeting these goals will require not just new technologies, but smarter ways of using them. Enter artificial intelligence. AI is emerging as a critical enabler in this energy transition. From predicting solar output to optimizing grid operations and managing battery systems, AI provides the intelligence layer that can turn variable, decentralized systems into reliable power networks. But AI is not a silver bullet. It's a tool, powerful but dependent on quality data, thoughtful design, and human oversight. In the parts ahead, we'll explore how AI is transforming the renewable energy landscape, making it more efficient, resilient, and ready for the future. Up next, a crash course in artificial intelligence: what it is, how it works, and why it's the key to unlocking renewable energy's full potential. Part 2: Basics of Artificial Intelligence. Smarts in the machine. Artificial intelligence, AI, is no longer a futuristic idea locked away in science fiction. It's here, it's real, and it's already shaping the world around us, from the recommendations we see on streaming platforms to self-driving cars and virtual assistants. But what exactly is AI, and how can it help us tackle complex challenges like clean energy? Before we explore how AI can power the renewable revolution, let's unpack what AI really is and how it works. What is artificial intelligence? At its core, AI is the simulation of human intelligence by machines. This means machines can perform tasks that typically require human thinking, like learning, reasoning, decision-making, recognizing patterns, or even understanding natural language. AI systems don't think like humans, but they can be trained to solve problems, make predictions, and automate decisions, especially when fed large amounts of data. Types of AI: narrow, general, and super. AI is often grouped into three broad categories. Narrow AI, weak AI. Designed for specific tasks, e.g., language translation, facial recognition, energy forecasting. This is the type of AI we use today in renewable energy systems. General AI, strong AI. A hypothetical AI that can perform any intellectual task a human can. It doesn't exist yet, and might not for decades if ever. Superintelligent AI. A level beyond human intelligence. Often the subject of sci-fi debates. Again, we're not there, and for now we don't need to be. In the context of renewable energy, we're firmly focused on narrow AI, intelligent systems designed to solve focused problems like predicting solar output or detecting equipment faults. Key subfields of AI. AI is a big umbrella, but here are a few of the most important components when it comes to energy applications. 1. Machine learning, ML. Machine learning is a subset of AI where systems learn from data. Instead of being explicitly programmed with rules, they find patterns and make decisions based on experience. Supervised learning uses labeled data to predict outcomes, e.g., forecasting wind speed. Unsupervised learning finds hidden patterns in unlabeled data, e.g., clustering similar energy usage profiles. Reinforcement learning learns by trial and error, e.g., optimizing when to charge or discharge a battery. 2. Deep learning, a specialized branch of machine learning that uses neural networks with many layers, hence the term deep. Deep learning is great for complex tasks like image recognition, e.g., inspecting solar panels for damage using drone footage. 3. Natural language processing, NLP, allows AI to understand and process human language. It's useful in interpreting maintenance reports, user feedback, or regulatory texts in energy management systems. 4. Computer vision, AI systems that interpret visual data, e.g., satellite images or thermal scans of wind turbines, often combined with drones for automated inspections. How AI learns, the data pipeline. AI systems are only as good as the data they're trained on. Here's how the typical process works. Data collection, sensors, weather stations, satellite imagery, smart meters, and more. Data cleaning and processing, removing errors, filling gaps, and organizing the data. Model training, feeding data into algorithms that learn patterns. Evaluation, testing how well the model performs on new, unseen data. Deployment, integrating the model into real-world systems like a smart grid. Monitoring and updating, continuous feedback keeps the system accurate over time. In renewable energy, this could mean training a model on years of solar irradiance data to predict the next day's energy generation with surprising accuracy. AI in action, simple example. Let's say a solar power company wants to predict how much energy its panels will produce tomorrow. Without AI, they might rely on simple equations or weather forecasts. With AI, the AI looks at years of historical weather data, solar production logs, satellite images, and even air quality levels. It learns complex relationships, like how cloud cover at a certain time of day or dust on panels affects output. It generates a prediction that's not only more accurate, but also dynamically improves over time. Edge AI versus Cloud AI. Cloud AI processes data on remote servers, great for heavy-duty computations. Edge AI happens on local devices, like sensors or smart meters, and is faster, uses less bandwidth, and is ideal for real-time decisions, like instantly shutting down a faulty wind turbine. In energy systems, combining both allows for responsive, scalable, and intelligent control over distributed assets. Limitations of AI. Despite its promise, AI isn't magic. It has limitations. Bias in data. If the training data is biased, so is the AI. Data quality. Garbage in, garbage out applies. AI is useless without clean, relevant data. Interpretability. Many AI models are black boxes, making it hard to understand why they make certain decisions. Ethical concerns. Decisions involving public infrastructure must be transparent, fair, and explainable. These are challenges, not roadblocks, and addressing them is essential as we integrate AI into critical systems like energy. A tool, not a replacement. AI is a tool, an incredibly powerful one, but it works best when paired with human expertise. It doesn't replace engineers, scientists, or policymakers. Instead, it augments their ability to make smarter, faster, and more sustainable decisions. Next up, AI meets energy. Now that we've laid the groundwork, the next part explores the exciting intersection of AI and renewable energy. You'll see how this fusion is already reshaping the way we forecast weather, optimize power grids, and keep critical infrastructure running smoothly. Part 3. The intersection of AI and energy. When intelligence meets innovation. The energy sector is undergoing one of the most dramatic transformations in its history. The old model, centralized fossil fuel plants feeding power to passive consumers, is being replaced by decentralized dynamic networks of renewable energy sources, prosumers, producers plus consumers, and data-driven infrastructure. In this new landscape, artificial intelligence is becoming the brain that makes the energy system smarter, faster, and more efficient. At the intersection of AI and energy lies an enormous opportunity to solve renewable energy's biggest challenges: intermittency, grid stability, storage optimization, and more, by leveraging the power of data and intelligent automation. Why AI is a perfect match for renewable energy. Let's be real, renewable energy is a bit unpredictable. Solar panels don't work at night, obviously, and their output drops on cloudy days. Wind turbines can sit idle during calm weather. Energy demand varies by the hour, the day, and the season. Traditional energy systems struggle to keep up with this variability. They were designed for steady output and one-way flow, from power plants to consumers. But renewables require agility, prediction, and real-time adaptation. That's where AI comes in. It excels at pattern recognition, decision-making under uncertainty, real-time responsiveness, learning from massive datasets. In short, AI provides the intelligence that makes complex energy systems work seamlessly, even when the inputs are volatile. Key applications at the intersection. Let's take a closer look at how AI is already transforming the energy landscape. 1. Forecasting renewable generation. AI models trained on weather, satellite imagery, and historical generation data can predict solar and wind output with remarkable accuracy. Google DeepMind worked with the U.S. energy firm X to improve wind power forecasts by 20%, helping the grid plan more effectively. AI tools can predict not just if it will be sunny tomorrow, but how much solar energy a specific panel will produce at 3:15 p.m. 2. Smart grid management. A smart grid uses digital communication to monitor, predict, and optimize the flow of electricity. AI plays a huge role here, balancing supply and demand in real time, detecting anomalies like outages or equipment stress, automatically rerouting power to where it's needed most. 3. Load forecasting and demand response. AI models help utilities anticipate when and where electricity will be needed, down to individual buildings or neighborhoods. This helps avoid blackouts during peak demand. AI can also trigger demand response programs, adjusting appliances or systems to lower load when necessary, e.g., turning down AC slightly during a heat wave. 4. Energy storage optimization. Storage systems like batteries are essential for stabilizing renewable energy, but managing them is tricky. AI helps predict the best times to charge-discharge batteries, extend battery life through smart cycling, coordinate multiple storage systems across regions. 5. Predictive maintenance. AI can analyze sensor data from turbines, panels, or hydro plants to spot signs of wear or failure before they cause a breakdown. Saves money on emergency repairs. Minimizes downtime. Increases system longevity. The rise of prosumers. Thanks to rooftop solar panels, electric vehicles, and home batteries, everyday consumers are becoming producers of energy too, aka prosumers. AI helps manage these microgrids by coordinating energy sharing between homes, predicting when EVs will charge or discharge, managing home energy systems based on time of use pricing. As millions of devices come online, AI becomes the orchestration engine that keeps everything running smoothly. AI at every level of the energy ecosystem. AI's role in renewable energy isn't limited to one area. It's woven through the entire ecosystem. It's like upgrading the nervous system of the entire energy infrastructure, with AI acting as the brain. Big players and projects. Several tech giants and startups are already combining AI with renewable energy in powerful ways. Google DeepMind, boosting wind farm revenue using machine learning predictions. Tesla, using AI to manage its Powerwall and PowerPack systems in homes and grid-scale projects. Siemens, deploying AI for predictive maintenance in wind turbines. AutoGrid, AI-driven energy management for utilities and grid operators. These are just a few examples. Hundreds of energy tech startups are using AI to carve out solutions in areas ranging from microgrids to blockchain-based energy trading. Benefits of AI integration: higher efficiency, extract more energy from the same resources. Cost reduction, cut operational costs through automation and optimization. Grid stability, keep the lights on even during disruptions. Lower emissions, faster and smarter transitions away from fossil fuels. Challenges and considerations. Of course, AI isn't plug and play. There are real concerns. Data privacy, especially with smart meters and consumer behavior tracking. Model transparency, why did the AI make that decision? Can we trust it? Equity, will AI-powered energy systems serve everyone fairly or deepen digital divides? As AI becomes embedded in energy infrastructure, ethical and policy frameworks will be critical. Conclusion: a smart partnership. AI is not here to replace human decision-makers, it's here to empower them. In the fight against climate change and the race to build a sustainable future, AI is our co-pilot. It brings speed, insight, and scale to one of humanity's biggest challenges, creating a clean, resilient, and inclusive energy future. Next up, Part 4, Forecasting and Prediction. We'll dive deeper into one of AI's most impactful applications, predicting renewable energy output, demand, and weather with remarkable precision. Part 4, Forecasting and Prediction. Seeing the future, to power the present. Forecasting may not sound glamorous, but in the renewable energy world, it's everything. Accurate predictions are the backbone of a clean and reliable energy system. With fossil fuels, energy generation can be controlled, burn more gas, get more power. But renewables, they don't follow orders from human operators, they follow the weather. Enter AI. Artificial intelligence has transformed forecasting from an educated guess to a precise, data-driven science. With AI, energy systems can predict when the sun will shine, how strong the wind will blow, and how much power homes and businesses will use, down to the hour, the street, even the device. Let's explore how AI makes this happen, and why it's revolutionizing the energy game. The forecasting trifecta. There are three main types of forecasting crucial for renewable energy systems. Weather forecasting, renewable energy generation forecasting, energy demand forecasting. Each plays a unique role, and all benefit tremendously from AI. AI for weather forecasting. Weather is the single biggest variable in renewable energy generation. While meteorologists have been forecasting weather for decades, AI supercharges this process by ingesting huge amounts of data: satellite imagery, radar readings, humidity, temperature, wind speed, solar irradiance, and more. Identifying subtle patterns humans might miss. Updating predictions in real time as new data flows in. Example: IBM's Deep Thunder system combines traditional weather models with AI to create hyperlocal forecasts, sometimes accurate to a city block. This level of precision is game-changing for solar and wind farms, which can schedule operations based on minute-by-minute weather changes. 2. AI for renewable generation forecasting. Using weather data is just the beginning. AI models can predict exactly how much energy will be produced by a specific solar panel, turbine, or hydro station. How it works. AI learns the historical performance of each asset. It correlates this with past weather conditions. It incorporates current environmental data, like dirt or snow cover on panels. It then predicts generation output for the next hour, day, or week. This allows energy providers to plan grid loads in advance, Trade energy more efficiently. Reduce reliance on backup fossil fuels. Case in point, Google DeepMind used machine learning to improve wind power forecasts in the U.S. Midwest. The result? A 20% increase in the value of wind energy by making it more predictable and thus more useful to grid operators. 3. AI for energy demand forecasting. It's not just about predicting supply, it's about anticipating demand. When will people use electricity? How much? Where? AI systems consider historical usage patterns, time of day and day of week. Weather, hot days mean more AC. Behavioral patterns, holidays, events, remote work trends. Economic activity. Real-time sensor and smart meter data. Why it matters. Accurate demand forecasting helps utilities avoid blackouts, manage pricing, and reduce wasted energy. It also informs demand response strategies, like reducing usage during peak times or shifting loads to off-peak hours. Real-world example. In Tokyo, AI-powered demand forecasting helps the city anticipate spikes in energy use during heat waves, allowing for preemptive measures like voltage adjustments or activating storage systems. Short-term versus long-term forecasting. AI supports both short-term and long-term planning. Technologies behind the magic. Here are some of the key tools and techniques AI uses for forecasting. Neural networks, especially recurrent neural networks, RNNs, and long short-term memory, LSTM networks, which are great at handling time series data. Gradient boosting machines, GBM, like XGBoost and LightGBM, popular for structured data and known for their accuracy. Ensemble models, combine multiple models for more robust predictions. Hybrid models, mix physics-based models with AI predictions, common in weather modeling. Some systems also integrate satellite AI and remote sensing for monitoring cloud movement, wind shear, or thermal signatures from space. The business case, why forecasting pays off. Forecasting isn't just good science, it's good business. Reduced operating costs, schedule staff, equipment, and storage more efficiently. Better market trading, sell excess energy when prices are high, buy when low. Improved grid stability, avoid brownouts or overloads. Lower emissions, reduce the need for backup fossil fuel plants. In some regions, accurate AI forecasting can mean the difference between profit and loss for energy providers, especially in competitive markets with fluctuating energy prices. Challenges and considerations. Despite its power, AI-based forecasting isn't perfect. Challenges include data quality. Dirty or missing data can throw off predictions. Model overfitting. AI can sometimes memorize the past instead of learning general patterns. Edge cases. Unusual weather events like wildfires or polar vortexes can stump even the best models. Infrastructure gaps. In regions lacking sensor networks or data sharing systems, AI has little to work with. These challenges are being addressed with more robust datasets, transfer learning, and investment in sensor infrastructure. The future, forecasting in real time everywhere. Looking ahead, AI forecasting will become even more advanced. Edge AI forecasting. Real-time predictions made directly on devices in the field, like a turbine or battery system. Swarm intelligence. Distributed AI systems learning collectively across multiple locations. Quantum AI. Faster, more accurate models that could forecast entire grid dynamics instantly. In time, forecasting may become so precise and widespread that energy systems will operate with almost no surprises at all. A huge leap forward for stability, efficiency, and sustainability. Conclusion: from uncertainty to confidence. In a world powered by the unpredictable forces of nature, forecasting is the key to confidence. Thanks to AI, renewable energy is no longer a gamble. It's a calculated, intelligent system capable of adapting in real time. Whether it's the sun rising tomorrow or millions of people turning on their air conditioners, AI helps us prepare, not react. And that makes all the difference. Next up, Part 5, Smart Grids and Energy Management. We'll explore how AI turns traditional power grids into intelligent self-optimizing networks ready for the renewable age. Part 5, Smart Grids and Energy Management. Rewiring the grid with intelligence. The electric grid is one of the most complex machines ever built. For over a century, it's done its job, delivering power from centralized stations to homes and businesses. But here's the thing. The old grid was designed for a different world, one with fossil fuels, predictable output, and one-way flows of electricity. Renewable energy changed all that. Today's grid needs to handle millions of new energy sources, like solar rooftops and wind farms, two-way flows of electricity, volatile supply and demand, and billions of data points per day. It's no longer just about power delivery, it's about smart energy management. That's where AI comes in. It's turning our aging grid into a smart grid, a living, learning, self-regulating ecosystem. What is a smart grid? A smart grid is an electricity network enhanced with digital technologies, like sensors, real-time communication, automation, and most importantly, AI. It can monitor its own health in real time, balance supply and demand dynamically, integrate diverse energy sources, solar, wind, hydro, batteries, prevent and respond to outages automatically, empower consumers with data and control over their usage. In short, a smart grid thinks, learns, and adapts, much like the brain of a complex organism. Why the old grid doesn't cut it anymore. Traditional grids were centralized, power came from a few big plants. Predictable, fossil fuel output could be tightly controlled. One-directional, electricity flowed from plant to consumer. But renewables introduce decentralization. Energy now comes from millions of sources, homes, businesses, even cars. Intermittency. Solar and wind are variable by nature. Two-way energy flows. Consumers can also be producers, prosumers. Without intelligent coordination, this complexity becomes chaos. That's where AI-powered smart grids shine. Key AI-driven functions in smart grids. Let's break down how AI enables a smarter, more resilient grid. 1. Real-time monitoring and diagnostics. Smart sensors collect continuous data on voltage and frequency, equipment temperature, load levels, and power quality. AI analyzes this flood of data to detect anomalies, e.g., a transformer overheating, predict failures before they happen, suggest maintenance or rerouting. Result: fewer outages, quicker repairs, lower costs. 2. Demand-side management. Instead of just supplying energy, smart grids manage demand too. AI predicts when and where energy will be needed, and automates responses such as slightly dimming streetlights during low traffic hours, adjusting industrial loads during peak times, encouraging households to use energy when it's cheapest or cleanest. This reduces stress on the grid and helps flatten demand curves. 3. Distributed energy resource (DER) management. From rooftop solar to EV batteries, modern grids must juggle millions of small energy sources. AI orchestrates these DERs like a conductor with an orchestra, ensuring balanced power flows across the network. Storage systems charge-discharge at optimal times. Energy is used where it's most needed. Think of it like a traffic control system for energy. 4. Outage prediction and fault detection. AI can detect early warning signs of equipment wear, line faults, overload conditions. It can then alert human operators, automatically isolate a faulty line, reroute power instantly. Example: during storms, AI systems can predict which parts of the grid are at risk, allowing utilities to act preemptively. 5. Renewable energy integration. AI manages the variability of renewables by forecasting generation, matching it with flexible demand or storage, ensuring the grid remains stable as renewables ramp up or down. Without AI, integrating high levels of solar and wind becomes risky. With AI, it becomes fluid and reliable. 6. Dynamic pricing and smart billing. AI supports real-time energy pricing, which can reward users for shifting their usage to off-peak times, reflect supply and demand fluctuations, help consumers save money while reducing emissions. Your thermostat could lower the temperature slightly when energy is cheap and clean, all automatically. Tech behind smart grids. A smart grid is powered by a cocktail of technologies, all made smarter with AI. Together, these systems enable microsecond-level decision-making across the entire grid. Benefits of AI-powered smart grids: greater reliability, faster detection and response to faults, efficient integration of renewables, balancing supply and demand with precision, reduced energy losses, smarter routing, reduced waste, lower emissions, better use of clean power, less reliance on backup fossil fuels. Consumer empowerment, real-time usage insights, control and savings. Smart grids around the world. Germany, leading in decentralized energy systems and smart grid pilots. China, investing heavily in AI-based load balancing and smart distribution. United States, smart meters and grid modernization initiatives across dozens of states. India, using AI for rural electrification and integrating rooftop solar. Netherlands, AI platforms that help residents trade solar power locally. Each country is adapting AI to fit its energy mix, policy, and infrastructure, but the direction is the same: smart, clean, resilient energy networks. Challenges in smart grid AI. Cybersecurity. A smarter grid can also be a bigger target for attacks. Data privacy, especially with real-time household usage data. Interoperability. Many systems, many vendors. AI must bridge the gaps. Scalability. Models that work in one region may not apply in another. AI offers solutions, but also demands careful governance and trust building. Conclusion: the brain of the energy system. A smart grid is more than just wires and transformers, it's an intelligent, adaptive organism. And AI is its brain. As we add more renewables, more devices, and more demands, AI keeps everything in sync, optimized, and resilient. We're no longer just generating power. We're managing ecosystems, and AI is our smartest ally yet. Next up, Part 6: AI and Energy Storage Systems. We'll look at how AI is revolutionizing batteries and storage, from predicting charge cycles to balancing massive battery farms. Part 6: AI and Energy Storage Systems. Energy's safety net just got smarter. Renewable energy is clean, abundant, and frustratingly unreliable. The sun doesn't shine at night. The wind might stop blowing when demand peaks. That's why energy storage is the secret weapon of the clean energy revolution. It's what keeps the lights on when nature takes a break. But storage isn't just about throwing a bunch of batteries in a warehouse. It's about timing, efficiency, health, longevity, and system-wide orchestration. Enter artificial intelligence. AI is transforming energy storage from a static backup plan into a dynamic, intelligent asset. It helps decide when to charge, when to discharge, how much to store, where to route energy, and how to protect system health, all in real time. Let's break down how AI is making energy storage systems smarter, faster, and cleaner. Why storage is critical for renewable energy. Before we dive into AI's role, let's zoom in on why storage matters in the first place. Intermittency. Solar and wind can't guarantee constant output. Peak demand. Energy use surges at certain times like evening, often when renewables dip. Grid stability. Sudden changes in supply or demand can crash the system. Energy shifting. Store clean energy during the day, use it at night. Storage helps solve these, but only if it's smartly managed. That's where AI comes in. AI's role in energy storage systems. AI enhances storage systems across 5 critical areas. 1. Predictive charging and discharging. AI analyzes weather forecasts for solar wind output, grid demand forecasts, market prices for electricity, current and historical usage trends. Then it decides when to store energy, e.g. during midday solar surplus, when to release it, e.g. during evening peak prices. Result: max revenue, max efficiency, and no wasted energy. 2. Battery health management. Batteries degrade over time. AI can monitor internal temperatures, voltage, and cycle data, predict degradation trends, adjust operations to extend lifespan, e.g., avoiding overcharging or deep discharges, suggest maintenance or replacements before failures occur. Think of it as a doctor constantly checking a battery's vital signs and prescribing preventive care. 3. Storage system optimization at scale. In utility-scale storage farms, think fields of batteries. AI coordinates all units to balance loads across systems, prevent bottlenecks or overuse of certain modules, react instantly to grid changes, e.g. frequency dips, scale power delivery across multiple locations. This is grid orchestration in action, and it's AI's specialty. 4. Market participation and energy trading. AI helps storage systems play the energy market like a pro. Predicts electricity price spikes, discharges stored energy when prices peak, buys energy to recharge when prices are low. This turns batteries from cost centers into profit-generating assets. 5. Integration with distributed energy resources, DERs. In homes or neighborhoods with rooftop solar and EVs, AI manages when batteries store home solar energy, decides when to feed excess energy into the grid, coordinates with EVs, some of which act as storage too, balances local microgrids automatically. It's how AI creates self-sustaining energy communities. Types of storage AI works with. While lithium-ion batteries dominate, AI supports many storage technologies. Whatever the tech, AI acts as the brain, ensuring the energy doesn't just sit there, it moves, reacts, and supports the bigger picture. Real-world example: Tesla Megapack plus AI. Tesla's Megapack battery farms come equipped with AI-powered software that coordinates charging across hundreds of units, responds instantly to grid needs, predicts energy prices, handles blackouts by acting as a backup generator. In South Australia, one of the world's largest battery installations, Tesla plus Neoen cut costs and stabilized the grid faster than any fossil fuel backup. How AI decides, under the hood. AI storage uses tools like reinforcement learning, learns optimal charging strategies through trial and error. Time series forecasting, predicts future energy prices, demand, and weather. Multi-agent systems, models where many AI agents manage individual batteries but coordinate as a team. Fuzzy logic, handles uncertainty, e.g., it might rain, what's the best move? AI makes these decisions every second, faster and more accurately than human operators ever could. The circular feedback loop. Storage plus AI creates a feedback loop. AI forecasts weather and demand. It schedules optimal storage activity. The system stores and releases energy based on this plan. AI monitors results and learns from performance. It adjusts future decisions for even better outcomes. The more data it gathers, the smarter it becomes. Challenges and considerations. Over-reliance, blindly trusting AI decisions without human oversight can lead to issues. Cybersecurity, AI-controlled storage is a critical asset, making it a target for hackers. Model drift. AI predictions can degrade over time without retraining. Regulatory barriers. In some regions, energy storage can't participate freely in energy markets. AI brings power, but also responsibility. Looking ahead, I+ storage in the next decade. Vehicle-to-grid V2G. EVs acting as mobile battery banks, AI managing millions of them. AI-driven microgrids, neighborhoods sharing energy autonomously. Global storage networks. AI linking storage across time zones for 24/7 clean energy availability. Self-optimizing systems. Storage that upgrades its strategy continuously without human input. AI and storage together will turn renewable energy from reactive to proactive. Conclusion: batteries that think. In the renewable world, energy storage is the safety net. AI turns that safety net into a strategic, profit-making, system-balancing powerhouse. Whether it's balancing the grid during a heat wave, maximizing solar ROI, or stabilizing entire cities, AI ensures our stored energy is always in the right place at the right time for the right reason. And that's not just smart, it's revolutionary. Next up, Part 7: AI in Wind and Solar Optimization. We'll dive into how AI squeezes every drop of efficiency from renewable energy farms, adjusting turbines, tracking the sun, and predicting cloud shadows. Part 7: AI in Wind and Solar Optimization. Making every ray and gust count. Solar panels and wind turbines are at the forefront of the renewable revolution, but they don't always work at their full potential. Cloud cover, wind direction, dust accumulation, suboptimal alignment, and system inefficiencies can lead to serious losses in performance. That's where artificial intelligence comes in. AI turns passive solar panels and wind turbines into intelligent adaptive energy generators. It helps them see, think, and act, extracting every possible watt from the environment. Let's take a closer look at how AI optimizes wind and solar energy production, from forecasting and alignment to maintenance and energy trading. Why wind and solar need optimization? Solar power is limited by sun angle, shading, dirt, and real-time weather. Wind power is sensitive to wind speed, direction, turbulence, and mechanical wear. Both generate variable and non-dispatchable power, meaning output can't be perfectly controlled like fossil fuels. Small inefficiencies, just 2 to 5%, can lead to massive financial losses over time. AI helps squeeze out every bit of performance by predicting, adjusting, and automating processes continuously. How AI optimizes solar power systems. 1. Solar irradiance forecasting. AI models predict cloud movement via satellite plus ground cameras, sunlight intensity over time, temperature impacts on panel performance. These forecasts help grid operators balance loads, prepare backup storage, optimize battery charging. Example: a solar farm can preemptively ramp down if cloud cover is detected approaching, helping avoid sudden voltage dips on the grid. 2. Dynamic tracking systems. AI powers solar trackers that adjust the angle of panels to follow the sun in real time. Uses computer vision and weather inputs. Adjusts tilt to maximize light absorption. Considers wind speeds to avoid damage. Result: up to 25 to 35% more energy than fixed panel systems. 3. Dirt and degradation detection. Dust and debris reduce solar output. AI uses drones plus computer vision to scan panel surfaces, machine learning to detect soiling patterns, optimization algorithms to schedule cleaning. Savings tip: instead of cleaning every panel regularly, AI pinpoints the dirtiest ones and triggers cleaning only when needed. 4. Performance monitoring and fault detection. AI continuously monitors inverter efficiency, Panel degradation. Module connectivity issues. It detects performance drops before they turn into system failures. This predictive maintenance approach boosts uptime and cuts repair costs. How AI optimizes wind energy systems. 1. Wind pattern forecasting. AI models wind behavior using weather data, satellite radar ground stations, turbulence patterns, terrain analysis. It predicts turbine level wind speeds, direction shifts, optimal times for energy generation. This improves forecasting accuracy and grid stability. 2. Blade angle and yaw adjustment. Wind turbines rotate and tilt to face the wind. AI optimizes yaw control, rotation around vertical axis, pitch control, blade angle adjustment. It adapts in real time for maximum energy capture, reduced mechanical strain, optimal power curves. Imagine each turbine as a weather-sensing robot, learning how to tilt its blades just right every second. 3. Wake effect minimization. In wind farms, turbines in front create turbulence for those behind. AI uses computational models to predict wake interactions, adjust upstream turbines to reduce impact on downstream ones, coordinate power generation across the farm. Like a flock of birds flying in formation, turbines learn to fly smarter, together. 4. Predictive maintenance. AI monitors components like gearboxes, blades, generators, bearings. Using vibration analysis, thermal imaging, and acoustic data, AI detects microcracks, fatigue, imbalances. Before a turbine breaks down, AI can suggest repairs or downtime, saving millions in lost production. Hybrid optimization, wind plus solar together. In hybrid farms, AI balances output from both systems, aligns generation with storage and grid needs, predicts total